Okay, we're very happy to have Sylvie Méléard here to give her third talk.
Second.
Excuse me.
Okay, thank you. So remember, so I hope that you had a good weekend, and remember that in the first lecture we constructed coupling between our population processes and some processes which satisfy the branching property. And I finished by explaining the coupling between at the level of historical processes. Remember, the historical processes, they take into account all the paths of the individual alive until a certain time, and the HKT is a measure value process, and the values are path space stopped h small t. Okay, for HK small t. Okay, and here, so for H tilde KT, you have the branching property. So, and remember our goal was, so remember that our goal was in this framework from the PDE point of view, you are at equilibrium, okay, and concerning the stochastic point of view, you have this profile at time capital T, the time where we are living, and we are asking from the trait point of view, which trait are the ancestor of the individuals. And what we want to quantify and to describe is the path of the arriving. You pick an individual at random at time t, and you want to first, we will, with the spinal approach, we will quantify approximatively, when k is large, the trajectories from an ancestor to this individual trait. And we will also compute this in reverse time to know from the individuals alive at time t what are the ancestor traits explaining this profile at time t. Okay, so from the historical point of view, what we are looking for, we are in a large approximation point of view. So we will consider k tends to infinity. Our initial measure is Z0k, which describe the population process at time 0. And we will pick up at random one individual at time capital T. So, and we consider the lineage of this individual. So we take a test function phi, capital Phi, and we observe, which is a function, bounded function on trajectories. And we consider the HK capital T on phi, which describe the lineage of all individuals alive at time t, and we renormalize by the number of individuals living at time capital T, which is, we have seen, either you can write it as HKT1 or ZKT1 or NK capital T. So that's the number of individuals at time capital T. And with the coupling, so you have to prove that, but it's an immediate consequence of what we have seen above, is that this limit is also the limit of the same quantity with the branching processes, the historical branching processes. Okay. And so now we will compute what is this limit, and that will give the result to the. So what is the interest to couple with branching processes? Of course, is the branching property, and which is that we will be able to escape the initial condition in a certain sense, since we know that the branching property gives some linearity with respect to the initial condition that you can see from this expression. And that means that now we will consider only one initial individual, making k is equal to 1, and we will observe what happens for our population process when the initial condition is a direct measure on one trait x. What we are looking for first is the expectation starting from the direct measure on x, so one individual with trait x, of the population process. And so that means that I have different notation which are equivalent. So here we are in the branching processes setting. So I put tilde for all which concerns the branching processes. And so V tilde T is the set of individuals alive at time small t, and X tilde I T is the trait on this setting for the individual labeled by I, okay? And so the first formula we have to prove, so therefore, I think that for certain people here, this approach is classical, but we will first prove Feynman-Tax formula, which in a certain sense separate which concerns the growth of the population and the moving between birth and death. And and that says that starting from one individual with trait X, the expectation of the population measure on some function, a bounded function f, smooth function, is equal to the expectation. So here we are at the measure levels, the measure level. So Z tilde T is a measure. And here we have the expression, which is the expectation from X of f of xt. Xt will be the underlying moving process. That means that we have seen it's a drifted Brownian motion here, it's very simple, times this multiplicative functional, which is the expectation, the exponential of an additive functional, which, and you see here, you have the growth rate. Remember, we are in the branching setting, so the nonlinearity is replaced by lambda. One was the birth rate, and x squared over 2 was the intersect individual death rate. Okay. So there are many proofs of that, but if you want proof between probability and PDE, that you can define. You have two measures here. You have a first measure which is defined by family of measures, mu t, indexed by t, which is mu tf is equal to expectation starting from Dirac on x of integral of fy z tilde t of dy. And the second measure is the expectation of the exponential of integral from 0 to t of 1 minus x squared over 2 minus lambda ds times f of t. And here for this expression, you have we have some semi-martingale property exactly as I explained for the initial process zk. And one can prove that mu t is weak solution of certain equation. And here you can use Ito's formula to also prove that mu t is solution of certain equation. So here you use this formula. And one can prove that mu t and it's general, and mu t with solutions of so the PDE dt of mu t. So we have already seen it in the first lecture. Sigma over square of mu t plus sigma c d over dx of mu t, and you have the growth rate term plus 1 minus x squared over 2 minus lambda mu t.
Excuse me, Sylvie, could you please recall just what's the dynamic exactly of the process? What are the dynamics of the process? So what is the branching component?
So here you have the dynamics of the branching process. You have a birth at rate 1, cell division or birth. You have a death, which is at rate, if the individual has a trait x, the death will be at rate x squared over 2, but plus lambda, in fact. Since we have replaced the logistic nonlinearity by this eigenvalue number. Okay. So that's the death rate, and that's and you have this moving between the jumps. You move as a drifted branching function. Okay, that's called branching diffusion process. And so that exactly the equation we have studied in the first course, satisfied by v of tx, and we have seen that it was unique. I remember I wrote my solution of this equation, and it's unique as finite measure value function. Okay, the solution. And so we have uniqueness, which give you immediately this Feynman-Kax formula. They are other proof, more probabilistic proof. So now that's the first step. There is a particular function which plays a main role, which is the expectation starting from the direct measure on X of the total mass, Z tilde for the branching process. Okay. And so, of course, you have this expression, which is very easily, remember, XS is a drifted branching process, Brownian motion, sorry. So you can write explicitly the density and so on, and prove that M is very smooth. Okay. And also by from the Feynman-Kax formula, we can prove that MT of X for X in R and T positive is the unique strong solution of this equation, which is the dual of this one. Okay, that's very standard. And what you can observe is that now, if I compute, so I have this expression, I would like to compute the derivative with respect to t of the integral of mt of x times f of x dx. Remember that f of x, f is a stationary steady state of this dynamics. Okay, we have constructed f like that. And so we write, of course, we have, so we will write that it is exactly, and that's the integral, and we can, so f has very, remember, f is a Gaussian one, so you have good properties of integrability here. And so you can inverse integral and derivative, and you apply your expression. So you have sigma square over 2 times minus sigma c integral of dx mtf and plus the term of order 0 mtf integral. And then, of course, you will play by integration by parts, and you will have sigma square over 2 integral of mt times the second derivative of x plus c sigma first derivative of x plus 1 minus x squared over 2 minus lambda f. And here we are happy since we recognize exactly the property that the definition of f was exactly the function, unique function f, and depending on the properties of lambda, remember, such that this expression is 0. And so this quantity is constant. Okay, and in particular, m0 of x is 1, and then integral of m t of x f of x dx is equal to integral from f of x. We will play with that later. To sort of generalize Perron-Frobenius. You can see that like you have a property. There is spectral theory after that, but behind it. Okay. So that's a remark that we proved. And so we call it lambda. So I have no time to develop that because it's very technical, but it's an accumulation of this Sanoff transform, in fact. And we can, in this case, in this Gaussian case, we were able to obtain an explicit formula for mt of x. So that's really that's due. So we applied argument due to Fitzsimons, Pitman, and Yor on this specific functional. Remember that mt of x is a functional which depends on the Brownian motion. Okay, and so. But so it's tricky, but you can have an explicit for expression of mt of x that we will use later. Okay. Okay. So now I would have this historical point of view. And until here, we were at the level of fixed population at the fixed time, and now we want to come to the historical point of view. And the first property we can remark is that now we observe the population at time capital T. So we consider the individuals alive at time capital T, but we want to have an information on what happens for their traits in the past. And so here I consider the label, the trait of the individual, label I at time capital T, but at time small t. Okay? And so we have a similar expression. And I will explain the proof. Remember that I define what means x tilde it small t. It's a trait of the ancestor of I, which is living at time small t. And so we have to compute the expectation from one individual with trait x of the sum for I belonging to vital t of small f of x tilde I at small t. So we have first to understand how we can describe this quantity. So that is exactly, so we know that for an individual I alive at time capital T, there exists a unique ancestor at time small t. We write it J, and I can write JT, which is an ancestor of I at capital T. Okay, so here we have the sum for I belonging to V tilde capital T, and the sum for J. Alors, J is a label for individuals alive at time small t. So J belongs to V tilde of small t, of f of x tilde J t, indicator of J small t, ancestor of I at capital T. And so now I change the sums. I have the sum over J of V tilde small t and of f of x tilde jt times the sum of on I belonging to V tilde capital T and indicator of jt, ancestor of it. But now if I consider this quantity, what does it mean? You have fixed some individual with label J at time small t, and you sum on all the descendants of this individual, okay, which are with label I at time capital T, okay. So I can write that until that it's a number of individuals J from J which go from T to capital T. Now, when we can observe is that if you consider F tilde T, the filtration of the measure valued process Z tilde, it's generated by all the values Z tilde of ZS and some Borel sets. So we have that the expectation, what is the expectation of this quantity? What does it mean? That means that we fix the information in time small t and we compute the expectation of the number of individuals at times capital T. So here we have one individual with trait J. What is this? So the times that gets, we go from capital T from small t to capital T. So we have a time capital T minus small t. And so that's exactly M capital T minus small t of x tilde jt. And remember, MT of x is the number of individuals with at time t, starting from one individual with trait x. Okay, that was the definition. So now we are almost finished. So that we consider, we compute the expectation of, and so we can replace by what is written here, and we will condition by ft. And so that will be exactly tilde xjt times m minus t of x tilde j. Okay. That another way to write that is the expectation. So here that means that you integrate with respect to the population measure valued process at time small t now. All depends on small t. Okay, so it's exactly z tilde t integrating f times m capital T minus t. I remember that another way to write the duality between measure and function. I use a different way to write. But now we can use the Feynman-Kax, the initial Feynman-Kax formula, where it is here. Since we have exactly this expression with f replaced by f times m capital T minus t. Okay, and so we can write that it is. Sorry, here we have delta x. We are at the level measure, and now we are at the process exponential integral to 0 to t of. Oh yes. For convenience, I will write this function h of x. So remember, that's the Feynman-Kax, the usual Feynman-Kax formula. And now we use a Markov property. Remember that something I would like to write somewhere, perhaps here. Mt minus t of ft is exactly the expectation from xt of the exponential from 0 to t minus t of h of xs ds. Okay, and so that's exactly the expectation, the condition of exponential of integral for, I don't see if you see that, from small t to capital T of f h of xs ds times ft. Sorry, the previous lemma was it's written. It was here. Sorry, it's for a fixed t. Okay, so now we can replace. This is ft measurable, and then we will have here exponential integral from t to capital T of h of xs ds. Okay, that's the Markov property of x, the Markov property of the underlying process xt. Okay, and that, so it's, we have the result. Okay, so that, of course, it's easy to generalize it to a product of functions of this form with different times, t1, t2, tn. So we can prove that for any t1, tn less than t, the expectation from delta x of the sum over I in V capital T of f of x tilde I t1 f1 fm of x tilde I tn is equal, so exactly the same proof. You can generalize this expression where you have the exponential from 0 to capital T of h of xs ds time f1 of xt1, etc., fm of xtl. Okay? And here you begin to describe paths in the past. Okay? And now we have to go from such events which describe the states. Sorry, it's I. Yeah. No, it's X. The states of the lineage at different times T1, T2, Tm in the past for the individual I observed at time capital T. And so it's not hard to go from this expression to this one, where you consider all the trajectory from 0 to capital T, all the lineage. Okay, so you can do that by linear interpolation. So that's the simplest proof we have written. There are many very difficult proofs, especially in the papers of Hamilton-Jacobi. I have already spoke about, but this proof is easy. And so now we have an information at the level, so where we consider all the lineages of the individuals alive at time capital T. And this quantity is exactly this one. So we have this correspondence between the historical point of view or the branching processes point of view. Okay. So that's the first step. So now we are looking for our specific trajectory to fix an individual living at time capital T. And we will develop what is relatively standard and called spinal theory. That is that, so we have this expression. We have already one way to describe this expression with respect to the process XS. But now we have another one, which is that this quantity on the left is equal to m t of x, m capital T of x, times the expectation of the phi taken on the trajectory of some process y, which will be, you fix, of course, you fix an individual alive at time t, so you create a bias, because first the individual, you condition by the fact that this individual is alive at time t, okay? And so there is a bias, and you are looking for the trajectory of this individual. And so here y is an inhomogeneous Markov process, and its infinitesimal generator is given by this expression. Okay. So I think I give some references, perhaps other ones, but it seems that it has been developed by Hardy Harris and also by Bonce Delmas Marshall Tran, and so more recently in the PhD thesis of Aline Marguet, which was, so it's a more general point of view. So Aline Marguet was interested in the growth of population where the cells are growing. So it's a different approach, but he gave some very general proof of this theory in a more general context. So I think that it could be interesting for you to see a direct proof in this case. So I would like to keep this. It's not so easy, but essentially it's due to Markov property. So, okay, so to prove it, we will, so remember, so you see that this expression is equal to this expression over m capital T of x. And that means that it is equal to this quantity, this exponential. So you see that that is an exponential with this weight, this multiplicative weight, and divided by the expectation of this weight. Okay, the weight is the exponential from the integral from 0 to t of h of x s ds. And so we can introduce some measure which depends on t and x, which plays on the trajectories, phi's, and which is exactly this. That is, this is the expectation of the exponential from integral from 0 to t of h of xs ds times phi of xs s and t over the mt of x, but that I write, that's the expectation of this weight. So that's a form which is relatively standard to observe that. And so we would like to prove that under mtx, the canonical process as is this process, is an inhomogeneous. That's exactly what this result means. Homogeneous Markov process with generator GT. Okay. So first thing, so I'll take some time u which is less than t. Okay, and I take some test function f on CBR. And so exercise for young people. You can prove that if you consider under this measure with this weight, you can observe you consider the expectation of f of xt condition to fu. So here ft is the sigma field of xs. That's exactly the expectation of the first term condition on fu divided by the second term condition on fu. Okay. So that's computation. And f of xt condition on fu over the same thing that exercise. You can ask me in 2 days if you don't find. Okay, so now I will apply this formula. So I first compute the expression of the numerator. So I will condition. So here I can separate into parts. So you have the part integral from 0 to u, which will be f u measurable. Okay, and so I will call that n over b. So n will be equal to exponential from 0 to u of h of xs times the exponential of the expectation, sorry, of the exponential from u to capital T of h xs ds times f of xt condition on fu. And since u is less than t, I can also condition on ft. So what does it give? Xs ds times, so you have the expectation, and here you are, of course, f of xt. And what is the expectation of integral from u to capital T of h xs ds condition on ft? So you have a term exponential from u to t to small t of hs ds, okay, times the expectation of the integral from small t to capital T with respect to ft. And that's exactly what is written here, the term which is remaining. And we have computed here, it is m capital T minus T of xt. Okay. So we play with. Okay. So now we have two functions of xt, and we know very well the dynamics of xt, and times this multiplicative function. So we can compute it. So first, so we use what you f of xt. So first we write that n capital T minus T of xt. So that's we consider it between u and t. Okay. So that's f of xu times m t minus u of xu plus, so the integral between u and t of what? Of L. Remember, so L is the generator of x. So I could have written here. So it L is sigma 2 over 2 d2 dx2 minus sigma c d over dx. It's a generator of the drifted Brownian motion, okay? With variant sigma, sigma square, and the drift is sigma c. Okay? But I keep this expression capital L. Yes, oh yes, it was written here. Okay. So you are L of f m capital T minus t, but here, since m depends on t, you have an additional term, which is minus f of xt derivative with respect to t of mt minus t of xt. Sorry, we integrate between u and t, so I will take small s. Yes, plus martingale part, okay, Linkin formula. But now I have seen that mt is a solution of some second order partial differential equation here, and you see that you have an expression for dt dtm, okay? And in particular, if you consider minus dtm plus lm, so it's exactly equal to this quantity. So we have that is equal to f of xu m t minus u of xu plus integral from 0 to t. And here you have, so L of m t minus west. So we begin to recognize the expression given in the generator of JT. Since here we have f, so it's taken in on, I forgot to write xs, sorry. Taken on xs minus f of xs. And here you have, so L m of t minus s of xs, and the additional term is h plus, so minus h of xs m t minus s of xs. Okay, so ds plus martingale part. So that's a martingale between u and t. Huh? It's null at u, at time u. Okay. So now we are on the good direction. We have to multiply by this exponential.
Excuse me. Is there a effect of f of x as missing in the last term in this? So h times
yes, it's in the front of this expression.
so
yes.
That's like one.
Sorry.
Yeah.
Yes, I'm sorry.
Yeah.
You're right, because I just replaced this quantity by its value. Okay, thank you. So here we apply Ito formula. That's very easy. So what does it give? The first term is identical. So plus so integral from 0 u to t. So I will write Oh yes, I should integral exponential from integral from u to s of h of xv dv. So times. So what we have L of m f m t minus s. So I apply Ito formula on both this expression, this semi-martingale, and this additive process. Okay. So that gives me minus f of xs L m t minus s of xs. Here L operates only on m. Here L operates on the product fm. And you have minus h m t minus s of xs times f plus an additional term corresponding to the derivative of this exponential. And happily, it gives you what you wish. That means exactly h of xs m t minus s of xs times f of xs. So I will write on, sorry, plus h of xs m t minus s of xs f of xs. So I close ds plus some martingale part between u and t. Okay, that I don't write. Okay, so and now I am happy this expression disappears. And here it's not. So I come back to the expression of JT. So we recognize the numerator of this expression. Okay. And so finally, this quantity is equal to f of xu m capital T minus u of xu plus integral from 0 to t. So I will write the of exponential integral from u to s of h of xv dv time j at capital T minus s at s. That's the notation is small s here. Gs of f taken on xs. I forgot on xs here, sorry. Times the denominator m capital T minus s of xs ds plus. Okay. So now we have to consider this expectation condition on FU. This one can also move or not?
No,
that's a bad thing. What to do? No, I will rewrite. Don't worry, I will rewrite the expression here. No, don't worry. Don't worry. Right, I can summarize. Here we have exponential from 0 to u of h of xs ds times the expectation, the condition expectation. And here, so we have a first term, which is fu measurable. So f of xu m t minus u of xu plus sf of xs m t minus s of xs condition on fu. And the martingale part disappeared. Okay. So now you see that I forgot. I'm sorry. I forgot this term in the second expression. Since now I multiply by this, but you see that there is the exponential, the integral from 0 to u and the integral from u to t. So I have only to do that.
No, I think the second one, right? It should be from instead of u to s, it should be 0 to s, but it should still be u to t in the first. But the integral is inside the exponential, right? So exponential and then 0 to s.
Yes, that's true. Sorry.
Yeah.
This one, you're right. Okay. So now we have, remember that mt minus u of xu is equal to this expression, you see? So here, so I will have the expectation of the exponential from small u to capital T, condition on fu. And here we have the exponential from 0 to u. Okay. So here we have, finally, the first term will be the expectation of f of xu, or you can f of xu, it can be outside, but expectation of exponential, and from 0 to now capital T, that's the product of these two quantities of h of xv. Condition on fu. That's the first term. And so for the second term, you have to, it is condition on fu. So as before, you can condition first on fs. So there is some ds somewhere. mt minus s of xs ds. And here we will condition this quantity is fs measurable, but here we can condition I have to decondition. So mt minus s, this quantity is exactly the expectation of the conditional expectation with respect to fs of the exponential of integral from s to capital T. So here again, I can decondition and replace these two expressions by the exponential from 0 to T. Okay? Because s is greater than. Okay, so that so now I can write from integral from 0 to T. Okay? That's only conditioning. And so now I let you finish, but we are essentially finished. I have to divide by this. So you see that if I I consider this expression, so I have to divide by this quantity. And so if I divide the first quantity, the first term will be on f of xu. And in the second term, you will have exactly the integral, the expectation of integral of gs of f of xs ds condition on f. Okay, and that's exactly what does it mean that js is the generator of this process. That's okay. Well, it seems tedious, but honestly, with respect to other proofs, if you consider other proofs, that's really simple. That's Markov property. No, that's why I wanted to get the proof. Okay, so now we have our generator, which is so this process is called the spine of spinal process, and you know that it is biased by this mt of x, which computes the population, the macroscopic population size, the expectation of the population size, which gives, as I said, a bias since you pick up at random the individuals in the set of individuals alive at time t. So that's not new. So you can write the semi-group, and you see that the semi-group depends on this weighted and non semi-group, which has a mass, which is not with mass 1. Okay. So now we can. So what? Of course, we did that for. So I can come back for this formula for any x, and now we can come back to our first framework, and we have a population process Z0k, which will tend to f, the stationary distribution f. So we have to integrate. We are in the branching context. So when k tends to infinity, we can assume that this quantity, so the expectation from Z0k of this quantity will converge to the integral of this quantity with respect to f. Okay, So you see that there is a new measure which appears, which is a measure with density f mt of x, f of x. Okay. And so we can prove that for the numerator and for the denominator of the expression. And so that's really, we are in the branching framework. So all the trajectories are independent. And so we can apply a sort of law of large number. It's just a generalization of law of large number. You have initial individuals and you have independent trajectories. Okay. And so like that, you can prove that the limit when k tends to infinity and on the assumption that there is 0, k converges to f, to the stationary distribution f. The limit of this expression, so the which have in mind to describe our individual pickup at random at time capital T, is exactly this quantity. So we integrate the numerator and the denominator by this measure mt of x, f of x dx. And remember, we have computed it. We have seen that mtf has the same mass than f, that is lambda, our eigenvalue lambda. And so we have this expression which describe exactly what we wanted. That means now we are in our context with interaction. So, but asymptotically, we have the same exactly the same result. And the process was so you see that why the initial value is not distributed along f, but it is biased by this information that you have conditioned on the individual alive at time t, and this bias is here. That you don't have the probability measure f over lambda, but the probability measure mtf over lambda. So I am late. So now we can use the explicit value of mt of x, and we obtain an explicit form of gt of the semi-group. And you can observe that when capital T, so remember, and so you are at time capital T. And so when you consider T, which is very close to capital T, your generator is not far from a drifted Brownian motion. It's standard, since you know that the moving between jumps is a drifted Brownian motion. But if T minus T is large, if you are here, you are closer to an Orstein-Uhlenbeck process. Okay, but here you have the exact expression of the process. Okay, so you, of course, so it's a Gaussian process, and if so, you have this solution of this stochastic differential equation, and you know the initial value, and you can show that for any fixed t, yt is as a Gaussian law, and so you see that there is a sort of delay for any small time t. Remember that we have this, we pick up the individual at random in the stationary distribution. So at time capital T, you have this profile, which is a Gaussian law centered in minus c. So here you have a center minus c exponential to minus sigma, which is the typical value of the trait, times capital T minus c. And so you have also the variance, and you can compute the density, of course, and the derivative of the log of this density. So we have the trajectory in the direct sense, and remember, we wanted to know the trajectory. That was the question en passant at the beginning. In the reverse time, to know exactly where are the ancestor of the trait, the ancestor trait of our individuals. So, but I not have time to. So perhaps we will finish tomorrow. But tomorrow I wanted to begin another chapter which is completely independent. But so now we have seen that our process is an. So that's a film due to Piet Titran, where you see. Remember, we were in the moving framework, where it seems that we have this profile at equilibrium, and he has also the simulation in the first framework, where you see the speed of the environment, the speed c, and you see progressively how it works. That means that capital T is growing, okay? And you see the trajectory at the beginning, you only see the Brownian part, in a certain sense, the drifted Brownian part. And after that, you see that you have only specific trajectory which appears, because you have the death And so certainly you have a lot of coalescing trajectories here, and then in the past you have only a few ones. And so that's what now, so as I said, I would like to better understand is the reverse point of view. What is the trajectory? Well, how can I summarize this trajectory? And so we use the very well-known framework of reverse time trajectories in this diffusion processes framework which is due to Haussmann and Pardue in the 80s. And that you can compute the time reversal of the diffusion, which has this form, and it's given by this expression. Of course, you have some assumptions, but which are satisfied here. And that's why I computed the logarithm of the density of the initial process. Okay. And so here you make computation. It was not my fault. And you see that the drift term is exactly minus sigma times y. So it depends on it does not depend on t, not on small t and not on capital T. And so that's you see that the time reverse diffusion of y, so y was this inhomogeneous spinal process, but the time reversal process has a very, very simple equation, which is this equation. Okay. And so it's a very simple Ornstein-Lindbeck process. And then we have to compute, to conclude this part from in our setting with our population with interaction. So we have to introduce a sort of an action function on trajectories. We make the time reverse. And we can prove that effectively, so we have what we wanted, that is that if we consider in our interacting setting an individual pickup at random at time t, if in the asymptotic when k tends to infinity and z0 k tends to f, we have at the limit this expression where y is the Ornstein-Lindbeck process given here. Okay. So I'm finished. So tomorrow, before beginning another chapter completely different, I will give you some ideas of extension in other, because here it seems to be miracle and due to the fact that we consider drifted point motion because we have explicit computation and so on. And so we observe that this process is homogeneous, so independent on t. So you can make t tend to infinity. That's that can be interesting to think things like that. So of course it's very really related to the fact that you pick the individuals in the stationary steady state profile. That's of course due to that. But so tomorrow I will show you what are the main points to generalize this result to different dynamics between the jumps.